All right, welcome back, everybody. Let's go ahead and get started. So, first announcement for today is that Gradescope is almost ready to go, as in it'll be open later today. Soko let me know that he has everything set up. He just needs to run one final test, and so that you will be able to submit your assignments for grading later today. Okay, everybody's excited about that? So unless something goes really wrong, I will not be extending the deadline. But if something does go horribly wrong, I'll reassess that decision, okay? Any questions about homework one? Yes?
So are you going to give us the test cases that you failed or no? That's you have multiple test cases, right?
I don't know how, so I haven't had a chance to look at his setup, so. But yes, there should be, I'm assuming he's put in multiple test cases, and but I don't know if it's going to give the feedback, like specific feedback, or if it's just going to say, I know that's configurable, but I don't know what he has it set at. And if it's like really terrible for this assignment, we can adjust it for the next assignment. So, any other questions about assignment one, homework one? Okay, next thing. So papers, yes, go ahead.
I know you said that the name of the partition type was going to be graded by hand.
Yes.
Can you provide any more clarity on how specific or accurate it should be? Because like some people I know have pulled stuff from Wikipedia, some people I know have pulled stuff from, say, MMLS. And so what our text that is there or the length thereof may vary quite a bit.
Yep.
Okay, so what constitutes accuracy? Just as long as it matches something, it came from somewhere?
So let me think for a second. So if I remember correctly, in the sample output of the homework one description, it stated that each of the fields needed to be separated by a colon. Yes. Sorry, comma. As long as there is nothing in the partition type name that has a comma, to throw off our parsers, right? Then we'll just visually say, oh, yep, that's that. Yes, yep, we're good.
Pretty sure the information is looking at the as commas.
You're probably right. They have commas in it. So if you just grab the description without doing anything else, that could potentially cause some problems. But once you throw it into Gradescope, you should see that, right? You should be like, it should say that you're not listing the next value, which should be the start sector. It should say that the start sector is not correct, something like that. In which case you would understand that it's parsing your output incorrectly and you need to adjust your names. Fair enough? No? You don't like my answer? Just don't use commas, and that'll make both of our lives easier. Any other questions about homework one? Okay, okay, paper assignments. So paper assignments, the final paper assignments are on the website. In case you are for the one person that still hasn't signed up on Piazza in this class, you can always, up until the due date, decide that you want to do an extra paper report and let me know. And it's extra credit, right? I'm not going to dock you if you don't do it, and anybody should be able to do it at any point, right? Up until the due date. That's what makes sense to me. So if you're not happy with your paper assignments, the great thing about doing an extra report is you get to pick whichever paper you want. Because the first round of assignments, I had to do some kind of leveling so that we at least had some critical mass of people that had read each one of the papers. For the extra credit, I don't care. So if you got assigned a paper that you are really bummed that you didn't get to read, like my dissertation paper for 12 or something, then you can do an extra report on that one if that's what you want to do. Okay. But please check those assignments so that you know which paper you're doing. Okay, 2 calendar items. Next Tuesday, a week from today, we have what? Not the midterm. What do we have next Tuesday? Yeah, Special Agent Erin Gibbs from the FBI, and she's awesome. That is a lecture you do not want to miss. So it is going to be awesome. I will not be testing you on any of the things that she says, but to listen to an FBI agent talk about forensics, like that's going to bring home so many of the principles that we've been talking about. Rules of evidence, Fourth Amendment, all of that stuff. You will see. It's got to be part of her talk. Okay, so please come. Please be respectful. Don't break the law so she doesn't have to arrest you while you're in class. Guess that's not very funny. Okay. Okay. Second calendar item. What's a week from Thursday? The midterm. Please don't forget. Week from Thursday is the midterm. I'm not moving again. No. Okay. All right. Let's do some review. So last time we were talking about files, right? So tell me, what is a file? What's a file? Are y'all scared to answer because I said there wasn't a right answer? Yeah, what's up? What's that?
Data about the data.
I think you're thinking of metadata. Is that what you're thinking of? Above the data?
File like a data code. File is a bunch of bits and views that
Yeah.
are organized.
Yep.
And then there's data about the data describes the
Yes, so that was going to be my second question. There's 2 parts to a file, right? They both start with a C. What are they? The container and the content, right? So those are the 2 kind of things that we kind of confuse, and we call both of them a file when really they're kind of 2 different things, but without both of them, is it really a file? So yeah, very good. So it's a file is a large amount of information. Oh, and give me some of the important properties of a file. Like, why do we want to have a file? Why does a file exist? Yeah.
Persistence.
Persistence. Give me more words. That's a good word, but keep going.
I want something to exist after I restart my computer.
Very good. So we have data that we want to store, and we want to persist beyond this current session, beyond next week, and even possibly beyond the life of the machine that created that file, right? Very good. Okay. What are the, we already talked about that. We already talked about metadata. Where is file metadata stored? Yeah.
I think it's usually not necessarily stored with the file. Like, it can be stored with the file, but in other cases, it's not stored with the file. Like,
Yes.
it's managed by the OS.
Yes, exactly. So the operating system, or more accurately, the file system, which is a part of the operating system, it keeps track of the metadata and it stores it in a different location than the actual file itself. And we'll talk more about that today if we get to that part of the lecture. What am I thinking here? Yeah, so what you said was correct, though, that some file formats do store their own metadata that is separate from the file system's metadata in the actual content of the file as well. So yeah, very good. Okay. Okay, this one's a little bit harder of a question. So when using a sequential method to access files, remember we talked about 3 different methods of accessing files, sequential is one of them. What happens when you write data? Give me an example of something that uses a sequential access method. Please be kind. That's your hint. Yeah. Yes, tape, right? So sequential. You can't just pull the head off and go over there. Like, you have to actually sequentially seek in a linear fashion all the way to where the data is, right? So when you write data, what is a byproduct of writing that data? That is implicit, yeah. Yes, overwrites. No, there's a more accurate term for what you just described. Yes.
Yes, we're truncated.
Yes, it truncates the file. So not only, because if we were to overwrite an entire file, right, we wouldn't necessarily truncate it if we started at the beginning, but you always are truncating. I think I'm getting mixed up. Anyway, you know what I'm saying, right? Yes, no, whatever, doesn't matter. Okay. What is a directory? Don't ask Robert, he doesn't know. What's a yeah? Yeah, it's a mechanism that helps us organize things. And actually, contrary to Robert's belief, it does speed up access for the operating system than to have one directory with lots and lots of files in it. So yes, it's even more than organizing, there's one important component of a directory, which is that it ties a file name to a location on the disk for the metadata. And we'll get into more of the details of what that looks like in today's lecture. Okay, if you delete a file that a symbolic link points to, what happens? Yeah.
The link still exists, but it's
Yes, the link, yeah, very good. So it does point somewhere, but that location is no longer valid. So, but yes, you're right. So the symbolic link does still exist, even if the file it pointed to is gone. How does that differ from hard links? Yeah.
Hard link points to like where the data is. So if you delete a hard link to a file, the other hard link will still work.
Yes.
The file is only clear when you clear the hard links.
Yes. So down at the lower level, what happens? Yes.
hard link increments the reference count. When you delete the original file, the reference count goes down by 1, but it is still 1 because the hard link made it 2.
Yes, very good. Yes. Yeah.
Question. So what if you have a link pointing to a file? What if you replace that file with something else? Would it still be pointing to the file, but it would be a different one?
So the terminology to answer your question, we are going to talk about today. So if you can hold on to that question, and if I don't answer your question in today's lecture, remind me on Thursday. Okay? Great. Any other questions? All right, let's do this. Today, we are going to talk more about file systems, and hopefully the projector works today. So in order to talk about file systems in a way that we're not just talking about one instance of a file system, I want to first talk about this file system reference model. So this kind of allows us to talk about file systems at just a little bit higher level of abstraction, which will help us apply the principles that we learn by analyzing ext4 and applying that to other file systems that are structured completely differently. So here is the model, and this is all from the File System Forensics textbook, great book. So there are a few different categories in this model. First is the file system category. That might seem redundant, but it's not, because the file system category gives you general information about the file system, such as the size, layout, location of data structures, and the size of data units. And this is where you start. If you are if you're analyzing a file system, if you're an operating system reading in a file system, this is where you have to start, because all you know is that you have a bunch of blocks of data. You don't know how they're organized. You don't know where data structures start and end. You don't know any of that until you understand this information about the file system. Okay, the next category is the content category. This is the actual data of the files and the main reason for the existence of the file system, right? It is organized into collections of standard size containers. What I mean by that, we'll talk about more in just a minute, but blocks is really what we're getting at there. The third is the metadata category. We talked about that a lot last time, which is metadata is data that describes a file, except for the name of the file. So the file name is not considered metadata. Okay, but things like size, locations of the content, the times that it's modified, access control information, that is considered metadata category. So, that is considered metadata. So the next category is the file name category. Now we have this in a completely different category because it's stored differently than metadata. And in order to read in the metadata, we have to have a file name to that's how we access files, right? We don't open up a program that reads in a file and point it to a sector location, right? A logical block address of the disk. That's not what we do. We give it a file name. The operating system starts with a file name and then goes and finds the metadata such as a location, and then it can actually read it in. So that's why it's a separate category. But this is primarily a human interface mechanism, as we talked about earlier, such as the name of the file. Okay, the file name is, the contents of a file name are normally stored in a directory along with the location of the file's metadata. And we're going to talk about all our directories today and all this stuff. Okay, application category. This is the last of the categories in this reference model. The application category, what that refers to is a bunch of non-essential, non-critical operations that the file system can do. Basically, it's just a journal. So journaling, we're not going to cover this at all in this topic or in this course, but journaling helps make a file system more stable, but it doesn't provide any critical operation to the file system, right? File systems have to read and write and organize and all of that. This just makes it more efficient at doing all of that, more stable. Okay. All right, and that is our reference model, but we're gonna draw a picture of it to kind of help draw all these concepts together in your mind, okay? So we start with the file system category that has the layout and the size information. That is what tells us about the other, where we can find information of the other categories, right? Now, as we talked about the application category, that's the journal. Since that's non-critical, we're going to kind of de-emphasize that for this conversation, but we're going to go into all the rest of these categories. Okay, file name category. These should look very familiar. We work with file names all the time, right? So these point to where there is metadata about that file. The metadata, in turn, gives us addresses and other information that's critical about the file. Using that information, that is how we find the content of the file. Okay. Any questions about this model? Yes?
So file names are stored separately from metadata for the benefit of the performance of the operating system.
For the benefit of the performance of the operating system, yes.
Okay.
Yes. You don't look convinced. You have a lingering question?
No, it's so okay. So it's yeah. So it's like search for so you get files and then from that then you can look for them.
Yes.
When you're actually accessing.
Yeah. So the reason why is a lot of times you don't care about what file type it is or what its access. Well, the access permissions is I know this, but the access times, the modified that. You don't care about that when you're just trying to find the files, right? If all you're trying to do is navigate the file system, sure, you have to check the permissions, but really what you need is the full file name and its parents, right? You need to be able to get from the root of the file system all the way down to the file you're looking for. And if you're having, and that's why it's, that makes sense.
Performance of the operating system, but
is because of the way he uses.
Yes.
Okay.
Yes. Very good. Any other questions?
No.
Okay, so I think I mentioned this earlier, but in previous years, this course focused heavily on a file system called FAT32, which is great because it's somewhat simpler than more modern file systems, but it really hasn't been in use since Windows 98. Some iterations of FAT are still largely used on like flash drives, mostly for compatibility with different operating systems, but it's not heavily used. ext4, on the other hand, is the most widely used file system in the most popular operating system on the planet. So I thought it would be good, prudent, to kind of adjust the content of the course and talk about ext4. So that's what we're going to do. I will kind of refer to how things are different in FAT32 throughout our discussion, but none of that is going to be critical to your success in this class. I'm really just kind of throwing out references, okay? So let's give some background. What is ext4? First of all, ext was the first file system designed for Linux. The first iteration of Linux used another file system from which ext borrowed a lot of its features, but ext was the first one designed for Linux. And it heavily influenced how Linux handles file systems. ext and the other future iterations of it organizes a disk into blocks and block groups. These are two terms that you need to not think about twice in this discussion. You need to understand what a block is and a block group. If I throw it out there, if you have to be like, wait, what's that? You might fall behind just a little bit in the conversation. First of all, blocks are groups of sectors. FAT calls them clusters. But blocks is what we're going to call it in ext4 for a reason that's very apparent a little bit later on in this topic. Blocks are always going to be 1024, 2048, or 4096 bytes. Pretty much all disks. I haven't seen an installation of ext4 that doesn't have 4096 block sizes. That's very common. So all blocks have an address that starts at 0, and the smallest, a block is the smallest addressable space from the file system's perspective. Okay, let me just throw stuff around for a second. Now, once we get into actual blocks, we can access the contents of it, but that's a different data structure. We're talking about the file system itself. One unit is a block of 4096 bytes. Okay? Good? Any questions so far? Okay. Please tell me this didn't break in the process. Give me a second. Hopefully this works. All right, we're going pointerless today. Okay, the next is a block group, which is a set of blocks. That sounds intuitive, but it's a well-defined structure, okay? The size is configurable, but always has the same structure. Not necessarily the same size, but always the same structure, okay? And we're gonna talk about that more in just a second. Groups are also numbered starting at 0, but there might be some reserved space before group 0. I have an illustration in just a second to show you what I mean by that. Yeah, question?
When we say size is configurable for a block group, is that on a block group to block group basis or a configured for the file system?
The file system. So yeah, I'll reemphasize that in just a second with the illustration I have. Okay. Okay. ext4, just historical notes, was marked stable October 2008, And then in December 2010, Google announced that ext4 was going to become the default file system for Android, replacing YAFS. It was technically it's YAFS 2 was the official, but nobody cares about YAFS 2. Anyway, so this is where we're at, right? Linux uses it, Android uses it. This is no small deal that we're talking about ext4. Okay, so we've talked about the file system category. No, we're going to talk about the file system category so we understand how everything is laid out. Now that I've given you very high level information, so let's lay out a disk, okay? So here you see that I have at the very beginning of this partition a set of boot code. Now this is always going to be the same size. It's always going to be exactly 2 sectors or 1024 bytes, always. And then right after that, we might have some reserved blocks, but that's going to be, I don't think that's very common. At least that's the impression I'm getting in the readings I've done recently. Okay, so we have n blocks. All of them have the same size and layout for a particular partition. So if you partition one thing as ext4 and another, that the volumes are of different sizes, their block sizes and the number of groups, block group sizes and block group number might be different, but always within one file system, they will have this, you'll have the same size and each one always has the same layout, okay? All right, so let's take a look at what this layout really looks like. So inside each block group, there is this structure. Super block, group descriptors, data block bitmap, inode bitmap, an inode table, and then finally the data blocks. So you see that the green squares here, those only occupy one block, which is how many bytes? 4096. In most common, I mean, you can configure it differently, but for the most part, always going to be 4096 bytes, okay? So 4096, 4096, 4096, okay? Questions about this? Yes?
Wait, what would be the advantages and disadvantages?
We're going to talk about that, probably not today, but it affects file fragmentation. Is the high level answer. Okay. Good question. Any other questions? Yeah.
So why would we have reserved blocks?
Oh, I was afraid someone might ask that question. I don't remember. I did read it in the last week, but I don't remember. So I highly recommend the Understanding Linux Kernel, the 1,000-page book. Yeah, it'll tell you, and then some. Okay, any other questions? Did I see another hand? Okay, all right, so boot code. Oh, I thought I left that up. Oh, no, it's, so that these first two sectors here at the very beginning, it has a very specific purpose, obviously to boot the machine. So if the file system, so not every instance of ext4 has a kernel in it that can be booted, right? It could just be files. Doesn't necessarily have, it's not necessary to have an operating system installed on a file system. Think of like a flash drive. It doesn't have an operating system on it, but it has a file system to organize the files, right? So if the file system has an operating system kernel, the first two sectors might have boot code. Now, what determines that is basically just how it's set up. But in this instance, the boot code that's in the master boot record, the MBR that we talked about previously, what it will do is it'll pass off control to the boot code in these two sectors, and then it'll continue booting from there. But that's not actually as common as just having the MBR code know where the kernel is and to boot right into the kernel, rather than booting from the MBR to the file system's boot code and then to the kernel, okay? But that's why it's there. That's its purpose. All right, super block. Super block is what tells you everything about the file system. All those high level details as far as like how big everything is, where stuff is. And here's the interesting bit. So we talked in a previous conversation about what if the master boot record gets overwritten, the partition table gets overwritten. Well, in ext4, if something happens to the super block, you have it duplicated in every single block group. Now, the kernel, it only refers to block the super block in group 0, but the others there are there as a backup, just in case something happens. Okay. And here's some of the things that it stores. The block size, so how big each one of these blocks are. And you'll notice that it's kind of interesting that you don't know the block size until you're into a block. Right. Anybody see any issue with that? It's like the encoding of a HTML page is like 3 lines in. You're like, wait, I've already been decoding this. And now you finally tell me what the encoding is of the page? No? No? Okay. Moving on. Block size, the total number of blocks. That's for the whole file system. The number of blocks per group. So there's only one number. It's not saying, okay, this group has this many and this group has this many. No. You have one number of blocks per group. And then the number of reserved blocks before group 0. So again, this is kind of interesting that you're reading in the number of reserved blocks before you even get sequentially to the super block. I don't know how that works, but probably the kernel handles it, right? Okay, and the number of inodes, the total number of inodes, and the number of inodes per block group. If you don't know what an inode is, that's fine. We're going to go into more detail than you want to know about inodes. Any questions about the super block? Yeah?
That is 496. the super block.
Yes. Yes. The super block will always take up exactly one block. Any other questions? Yes?
The kernel know that something's wrong with super block.
You want me to pose a hypothetical scenario? Is that what you're asking?
No, it's like, is there a mechanism?
Yes.
Or the vector count is just there. Active attack. Next year.
I don't remember specific circumstances, just that I read about them.
Something doesn't.
I was like going fast and furious to create these slides. So the details like that, I was like, okay, yeah, we probably won't talk about that. Any other questions that I can't answer? I mean, I can. All right. So, yes, go ahead.
So the block size, but does it tell each of the other blocks the size of the like? I was just asking, like, what does the block size?
It means if it's 1024, 2048, or 4096 bytes. Yeah.
Oh,
So here, this might help. So this is an actual example that this guy posted to, he had this really great blog article about ext4. So you'll see that it includes a lot of this information. So the volume name really isn't critical. Last mounted on, let's see, block count. This, what's that? Yeah, block size right here, 4096. First block is 0, of course. Number of inodes, free blocks, I mean blocks that aren't being used to store anything. Blocks per group, inodes per group. First inode, okay, so this is 11. Basically, we're not going to go too far in depth to what that means, but usually 1, there is no inode 0. 1 through 10 are reserved for the system. So really the first inode that's usable by the file system is number 11. So that's pretty common. 256, this means that we're definitely using ext4 for reasons we'll talk about later. And yeah, so this is the output of the tool dump e2fs on an ext4 file system. So, any questions? Yes.
How do we determine, or what is like a good way to figure out how many blocks per group we should have? Because if we're going to be duplicating the super block every single group, that would seem like a lot of wasted space if that's too small. I mean, a lot. I mean, it's only 2 sectors. But.
So it's actually quite simple. So the inode, we're kind of, I hope this makes sense because we're doing things a little bit out of order, but the inode bitmap, not the inode, the data block bitmap. This lets you know whether the data blocks over here are being used or not, if they're allocated or free, right? This will always be the size of 1 block, and it will be equivalent, so 4096, and it will use every single bit. So 4096 bytes, so times 8 to get the number of bits, that is the exact number of data blocks that you'll have in one group. So if you have a smaller block size of 1024, then you will have 1024 data blocks in one group. And then there's some ratio for the number of inode entries that you have per data block, right? And so really it's once you know this information, this is actually, we'll talk about group descriptors in a second. This is pretty standard. This is configurable, but as a ratio, this is determined by that. So really, that's how you determine the size of a block group. And then from there, it's just arithmetic. Yeah?
Question. So if the first block, super block is over, you don't know what the block size is. How do you know when you get to the other blocks?
Great question. I don't have an exact answer for you. Other than that, I know that there are tools that know what they're doing and can figure it out. So, good question though. Any other questions? Okay, let's talk about the group descriptor, and then we'll take a quick break. Okay, so you might be wondering what is a group descriptor. That's kind of a funky term. So obviously we're talking about these groups, the block groups. That's where the group comes from. And then it has a bunch of fields that describes it. So basically the block numbers of the block bitmap and the inode bitmap. So this tells you, inside here, it tells you where this starts and where this starts, as well as the block number of the first inode table. So here, here, and here, and then you can actually calculate where this starts if you know this. So it doesn't actually store that, but it does tell you the number of free blocks, the free inodes, and the number of directories in this group. Okay. The descriptor table contains all the descriptors for the whole file system. So it's actually duplicated in every block group, just like the super block. So from here all the way to the end of the group descriptors is going to be the same for every block group in the file system. Okay. That I'm pretty sure is a matter of just efficiency, so head seek efficiency. So if you're clear down at the end of the file system and you're seeking for something for a particular inode number, if you know where the address is for a particular inode bitmap, you can do calculations without having to move the head to a particular group descriptor at the beginning of the file system. to then know where to jump to next. Does that make sense? Mostly, or not really? Yes, please.
Why wouldn't that just be like basically permanently in the RAM? Because that's not a lot of it.
You're asking such awesome questions. No, that's great. I don't know. I don't know. Maybe it is, but I don't think so. I think that the file system, please don't quote me on this because again, this is not one of the details that I had time to research. I think it's more important for the file system to have the directory structure in RAM than the group structure, because of all the path traversals that the operating system does up and down the file system. But I'm not sure, so I apologize. I don't know. Any other questions? All right, we'll go ahead and take a couple-minute break. Give my voice a chance to rest. Hey.
Hi. So if I'm getting the wrong checksum for that image, I noticed somebody posted something in Piazza about clearing your cache, and I've already done that. Is that something I should email the TA, post question Piazza?
So
I really
right. So
don't
you,
understand.
how are you calculating the checks?
I have a couple different algorithms that I've found. One of them does like a while loop and checks the length of my read-in file. And then the other one is a while my data is true or while it's still reading the file.
So it's actually in your code?
Correct.
Okay. So you don't have to do it that way if you don't want to.
Okay.
So you can actually call out to another subprocess to do the calculation for you if you want
Do the
to.
checksum for me?
So MD5 sum, SHA-1 sum, those are actual program names in Linux.
Okay.
You could just call them on the file, grab the output, and do that.
Now, that's kind of important to have the checksum, right? I don't want to continue on if I don't have the checksum right. Because like I've cleared my cache, I've re-downloaded the file too many times.
So try the SHA-1. Let's see. No, it
It's
was
a
SHA-256,
SHA-256.
right? So try using the SHA-256 sum utility on it first to verify the integrity of the file that you're downloading.
Okay.
If it's the correct file, then go on to the next part of the exam.
All right, cool. Thank you.
Yeah. Hey. Yeah.
I don't want to take
Thank you.
Well, you have to have very
Professor Baby. Can I get the? You know, I said something like you had to have, and then I was too late. Well, I have it. If I had questions about the project, you usually I know right, but you have things that you have across So okay, so I guess real quick. So
I gotta keep going. Yeah. We'll see. Okay, let's go ahead and get started again. All right, we were talking about file system category. So now we know the layout and the size information of everything in our file system. Now we can move on to the file name category, and that basically consists of directories. So we've talked about this before, that a directory is just another file, but it has a really simple structure that identifies the files that belong to that directory. Okay, in ext4, it will always include two special entries, the dot entry and the double dot entry. Dot points to itself, and double dot points to its parent. So even the root directory has a double dot entry. Where do you think it points to? It points to itself. Very good. Yeah. What did you say?
I was gonna say.
Yeah, the root. Yeah, it's very good. So here's some fields in a directory entry. So we open up, actually, I don't know if you've ever done this, but if you're in a Linux console and you open a directory in Vim, it actually shows you the contents of the file. It's kind of cool. So this is what is contained: an inode number, the file name, and the file type number. So this is not technically part of the file name category. This is strictly in the metadata category, but ext4 kind of cheats a little bit and stores information that really belongs in the inode, and it does live there, but adds it here in the directory entry. So here's an example of a directory entry. Oh, good, it came out right. I tested this earlier today, and when I was in presentation mode, the whole thing looked wrong. Like it was off the page and everything. So I'm really gotta look right. Okay, so here's what we have. On the left-hand side, this is the offset into the file. So at the very beginning, we have here a 4-byte entry, so that's why there's 4 squares here, telling us that this file its inode is inode 21. This record is 12 bytes long. Its name length is 1, so we know how much of the string to read in. The file type, which number 2 indicates that we're dealing with a directory kind of file. Sorry, let me talk about this really quickly. So these are the 8 basic file types in ext4. 0 is unknown. That is really just if a file becomes orphaned and there's not very much information known about it. That's really the only time that's going to be used. Regular file and directory, these are the 2 main ones. So number 1, regular file, 2, directory. That's really all you need to remember for now. Okay, so we're dealing with a directory here, and its name is dot. So this directory entry, where does it live? What is its inode number? This is not a trick question. Yeah.
21.
21. Inode 21. So this file lives so this is the contents of the file. Inode's the kind of the container, right? The container for the contents we're looking at right here is located at inode 21. Okay. And its parent address is 22. Yeah, so the double dot is the parent directory, right? Points to the directory entry that contains this file that we're looking at. Okay. So moving on, so we've got here another directory, file type 2 called home1. The name length is 1, 2, 3, 4, 5. You can see here that we actually have gone past the length of the other ones. Now the reason why I have that there is that these first fields are always going to be 8 bytes from the very beginning to where we start the name is always going to be a multiple of 4 bytes. So anytime we don't end right on a multiple of 4 bytes like we do right here, we have to fill it with /0, the null character. Okay? So this is the one that I want to talk about. So why do you think that the record length for starting at offset 40, why is the record length 28? This is a lot longer than these other ones that we've been looking at. Is it 28? Why is it 28? Let's count, right? So for this one, we could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is 16. If this is 16 over here, why do we have 28 for the length of this record? Where would 28 end us up? Where would we end up?
What are estimates?
Hmm?
At the beginning of estimate? For 40 plus 28.
So let's see. This would be 12, right?
Yeah.
12, 20, 28. Why would this record point to the end of the next record? Yeah.
The whole file was big marked as inode 0.
Is there an inode 0?
There should.
There isn't an inode 0. So this file right here has been deleted. So in this directory, what we do is instead of trying to like rearrange all these sequential pieces of data, which by the way could be millions of entries long, right? Potentially. Instead of rearranging all of that, what we do is we set this inode 0, and then we lengthen this field to just cover it up. So as we're reading in this entry, this record right here, we see that the name length is 3. All we're going to do is read in those 3 characters, then we're going to stop. If we want to get to the next entry, we would have to do the math to find where we should seek to next from this point in the file. Did I lose anybody? Does that make sense? Okay. So this one was deleted, and then there's also something interesting about this one right here. Why is sbin so long? What do you think? Yes? Exactly. So 4028 is the block size, 4096, minus the length of all the previous records. Why? That is how we tell the file system that this is the last entry in this directory. Easy enough, right? Okay, so this is kind of cool, right? I think this is kind of cool. Any questions about this structure? Yes?
So usually a file is but that entry, or like, is it going to get over?
No. Well, no. Yeah, good question. Yes?
Why is sbin not alternated?
Because it stops at a multiple of 4.
But how would I know that it stops at multiple, or if I don't check something else?
Right there.
Okay.
The record, the name length is what tells you how many to read in. The filling with null is really just, I don't know why. Yes, go ahead.
Wait, just to reiterate, is this supposed to always take up one block, or can this take up?
Ah, yes, so just like any file, a directory is just another file, right? So a directory can grow and grow and grow and grow to be gigabytes, potentially, right? Good question, yeah, yes.
Does it also have a entry for bill date for direct?
So that is a special thing that is, there's not actually any directory entry because it's unique to the currently logged in user, right? So it wouldn't make sense to have a relative path hard-coded into the actual directory entry like this. Good question. Any other questions? Yes?
Could you briefly describe what the inode is supposed to represent again?
We're going to talk about the inode in just a second. Like tons of information about the inode. Okay. But basically, that's where the metadata for the file lives. Okay. Did I see another hand? Okay. Fix this structure in your mind. You got it? Hold on to it. Ready? Throw it out the window. So I just learned this today, okay? That this linear array of entries is actually quite inefficient. So ext3 and ext4, they have this option of using a balanced hashed B tree that is keyed off of a hash of the directory entry name rather than it being sequential like that. So if I were to hypothetically ask you an exam question on directory entries, it would be about something like that looks like this. Hypothetically. But just so that you know, this is a thing. Like I said, this is something I learned literally today as I was fine-tuning my slides. Yes, question?
Do the entries look the same? Just their hash in order to?
Dude, I learned about it today, man. I took the day off of work to work on these slides, man. So I don't know. But the textbooks know. So if you want to check out the textbooks, they will have the answer. Yes.
So when you say that they can use a balanced tree, it doesn't necessarily mean that they do. It's
Right.
that they can.
So there's about 1,000 different levers that you can adjust when you create a file system. Just happens to be that there's a lot of really great defaults. This is probably one of them, but you can create an ext4 file system with this option turned off. And then your directory entries would all look sequential like the example we just saw. Okay? Any other questions? Okay, this is the moment you've all been waiting for, the metadata category, where we're finally going to talk about what the heck an inode is, right? Okay, so this beautiful diagram illustrates the relationship between a file name and a data block. You can't go from the file name straight to the data block. You have to have an inode in between to store all the metadata about the data block. Because here's the thing, this seemingly simple structure can suddenly transform into something that looks like this, right? Because we can have hard links, basically entries in other directories that point to the same inode. That's what a hard link is. A directory entry somewhere else in the file system that points to the same inode. That's kind of an important detail that you might want to take note of. And the inode can cover lots of different data blocks, right? If a file is fragmented, if a file gets moved, if file gets completely moved, not in the directory sense, but the content of the file can move, the inode stays the same. The inode stays the same whether it's in one file, one directory or another, whether it's pointing to 3 data blocks or more. This is the center point of the file system, right? That's what hooks all this stuff together. It allows us to be able to find things, store things, everything. Kind of important. Questions? All right, so I told you, more information about inodes that you wanted to know. And this is just slide 1. This is taken straight straight from, a lot of this information is taken straight from this awesome website, ext4.wiki.kernel.org. So kernel.org is where there's tons of information about the Linux kernel, right? This just happens to be one subsection of the wiki of that website. If you have questions about what I talk about with respect to inodes, I would recommend you go to that link to reread it. The Understanding Linux Kernel book is good, but doesn't include information specific to ext4. It's old enough that ext4 was not around. Same thing with the file system forensics book. Okay, and there are things that are very different. Well, not very different, but there are important differences between ext3 and ext4. Which again, we're going to talk about the details, maybe not today. But okay, let's talk about a few of these fields that are important for forensics. Okay. The first one is the mode. We're going to talk about what mode is in just a minute. But that is the first thing that is in the inode, which means that at least as far as headseek, well, the mode is the permissions on the file. Sorry, I'm getting myself in trouble for talking before I think through what I'm saying. Never mind, moving on. So here we have the owner's user identifier and the group identifier. Every file in ext4 has an owner, has a user ID of who owns that file, which may not be the same as the user that created that file, and a group that file belongs to. Is there anyone that's not familiar with the concepts of user and group from a file systems perspective? If not, that's okay. I'm realizing right now that I made that assumption that everyone knew what that was. Have all of you seen file system details like this before? Okay, all right. Some yes, some no. That tells me I'm at least not wasting time lecture. Okay, so we'll talk more about how this relates to the permissions in just a second. Here we have last access time, last inode change time, or just change time, last data modification time. So we talked, I don't remember which lecture it was, but we talked very high level about MAC, M-A-C, being important for forensics. So time attribute values, this is the M, A, and the C that I referred to. What is the epoch? Anybody know what the epoch is? Yes.
January 1st, 1970.
January 1st, 1970. I don't know the historical reasons beyond for that. I'm sure there's a really great story behind it, but that's what it is. Okay. So, number of seconds since January 1st, 1970, midnight, so 0000 at UTC, Universal Coordinated Time. That's what those mean. We also have a deletion time in seconds since the epoch, and hard link count. Every time we've talked about hard links and there being some reference counter, that's the field in the inode that I'm referring to. So you create a new inode, hard link, that goes up. So here's an important detail about that. When you create a new directory, let's say you're in the root directory and you create a new directory. Does anything about the inode of the root directory change? Just think about it for a second. What changes about the root directory's inode?
So each subdirectory has a reference to its parent, so I imagine they have some kind of link to the root directory, like maybe
That's a hard link.
Yeah.
It is a hard link. So this, which means that the root directory It points to itself, and it points to itself as its parent. So there's 2 hard links. Create a new directory, that's a 3rd hard link. Every new directory inside of the directory is going to increase that hard link count. Okay? This is important. You can't delete a file until this is 0. Okay? Yes?
Is that why you can't delete directories?
That is one of the reasons. That is one of the reasons, but that's not the only reason. If you look at, I think it was last lecture, we talked about operations on directories. We had operations on files and operations on directories. And deleting a directory is a different, it's a separate type of operation. And so it just doesn't make sense to combine the 2 into one, based from the file system's perspective. So that's enough. But yeah, it's insightful. Any other questions? Yes.
So it kind of says it on the slide, but is there a limit to the number of subdirectories that you can have?
There used to be. So with ext3, there was a hard limit of 64,998. With ext4, they figured out that what we could do is just not keep track after a certain point. That's basically what they said. You know what? It's just really high. Okay, our link count is really high. It's not going down in any time. We're just not going down today. So basically, it's set to 1 to indicate that the number of hard links is not known. It would never be 1 for a directory under normal circumstances, right? Because every directory not only points to, so the parent directory points to it, and it points to itself. Right? So every directory, no matter where it is in the file system, always has at least 2 hard links to it. So a directory will never have a value of 1, which is why they used it, to say, we don't know, but there's at least that many when we got to this point. Yes?
How does it handle getting out of 1?
I don't know.
Okay.
That's another detail I learned today, so I'm not an expert. So. You have another question?
That was good, let's ask that.
Fair enough. This isn't a file systems class, right? I know just enough about file system to do forensics on them, not enough to write my own file system. And so that's my caveat there. All right. Okay, the last one on this slide is the extent tree. So when we talked about logical volumes, remember I kept throwing around the term extent. Extent is logical, physical extent, and we have logical extent. And I told you, don't worry about it for now. Just think of it as a block of addressable spaces, okay? So we're going to talk about extents next time in depth, but basically it's just a sequence of consecutive blocks, okay? That's all you need to know for now. More fields. Oh, you thought we were done with this, right? No. So here's an interesting thing about ext4, is that it has a lower, no, not the size, it's the, I'm getting ahead of myself, but let's talk about this now. So on the previous slide, we said that there was a creation time, modified time, access time, right? Well, this is the extra information. Basically what they did was they said, you know what? With only 32 bits of data to count seconds from 1970, we're actually going to overflow our value in 2038. Kind of a problem, right? So what they decided to do was, as of ext4, yeah, ext3 doesn't have it. ext4, they added these extra fields. So as of any offset in this table that is greater than or equal to 0x80 is specific to ext4. Okay, what they did was they added extra 32 bits for each of these times, and the least significant, most 2 bits go to the second and the rest are nanosecond. Okay, so that gets us to 24 something, 24, 43, something like that. And then we have nanosecond, sub-second precision on all of these times. Okay. If I were to test you on that, I would first go through that in more depth in lecture, okay, with examples. Not going to happen today. Okay, but all right. Then we also have block counts and size, lower and upper 32 bits. File creation time. So this did not exist before ext4. So this, when we talk about time attributes in forensics, we almost always use MAC, right? Modified, access, and changed time. So it's usually, yeah, change time. And then, but there's also deleted time and created time that are separate, but not as common. I'm boring you, so we're gonna move on. Okay, I want to get to a couple more slides before we're done today. So, any other questions about this before we move on? I know this is kind of dry, but that's trying to understand the Linux kernel is just kind of like that. Okay, let's talk about mode, which is file permissions. So ext4 stores file permissions for the user, the group, and everyone else as by using 3 bits for each of those. Hopefully this isn't too new to you, but these 3 bits represent the read, write, and execute permissions. 1 means they can, 0 means they can't. So let's use an example. This example has the mode 0754. The 0 really just means that we're displaying this number in octal, not decimal. Why do we just do it that way? Well, because it's just easier. So the first, let's take the first one. The 7 corresponds to the user. So 111 for read, write, and execute means that the owner can read, can write, and can execute. All right. Next number, the 5, which translates in binary to 101, means that the group, if that's what position we're in, can read, cannot write, but they can execute on this file. And then finally, everyone else, the world, others, or translated to binary, 100, the world, everyone can read this file, but they can't write or execute to it. And that is mode. Any questions about mode? Okay. Last slide for the day, okay? We already talked about file types a little bit. The most important 2 types are which ones again? Yes, the regular file and the directory. So interesting thing, these are the only 2 types that actually allocate blocks of data. So character device, block device, those are external devices. So it doesn't make sense for us to allocate data on this file system. The name pipe socket, kind of the same thing. There's just a way to access stuff from the outside world. Symbolic link though, actually we can, so in certain circumstances we do allocate data blocks, meaning that if the path to the file that we're pointing to is less than 60 characters, that's small enough that we can actually store it right in the inode. We don't have to allocate a data block. So most of the time, that's sufficient to not need to allocate any data blocks. Otherwise we do, and then one more jump in the file system before we know where we're going. Okay, finally, block device, just as an anecdote. So block devices like, I hope you've heard that term, even if you don't understand what it is, I'm gonna tell you right now. Block devices require you to read and write a full block's worth of data at a time. You can't just read a single character and read it or write it out. If you do that kind of an operation, there's something sitting in the middle between you or your program and that device that is reading in a whole block, but then only giving you 1 character and then writing it out at a block at a time. Okay, that's just how they work. Hard drives are one of those kinds of devices. So block in this sense is a kind of an overloaded term because a block for a hard disk should be what? Sector, which is how many bytes? 512. How many bytes to a block in exe file for a file system? 4096. Okay. So there's a little bit of an overload term there, but okay. All right. Hopefully I didn't lose anybody. Thank you so much for sticking with me, and we'll see you on Thursday. I do have office hours today.